So today I continue to discuss analytical side of non-standard analysis, so it is analysis itself. Now we have more or less enough tools to formulate some things. Part of them are just illustration, parts are maybe new stuff. So first I want to consider distributions or their whole generalized functions. In non-standard analysis. You know what is distribution. So, for simplicity, let us consider functions on the circle S1 and consider the set space B equals C infinity of S1. Here we have no infinity, so we don't need different problems with the support of the functions. So it is the space of test functions. And the conjugate space is the space D prime distributions. Distributions are linear functionals which are continuous linear function of this space D which are continuous. Yes? So this means that if you have f in D prime and phi in D, then we have the bilinear form f phi, the scalar product, and this scalar product is continuous function on phi as element of this space. And here this space is the space with countably many semi-norm. No, semi-norm can be the supremum of modulus of a derivative of different orders. Yeah? And so if f in D prime, this means that there exists M such that f phi less or equal than C norm phi in Cm, for example. So these are each f is continuous functional in some space Cm. Yes? And this means that if f is like this, then f has the following form. Equals integral over S1 some function f capital of x this way, where fx is integrable function. So this way we restore the general form of a distribution. Now, on the line, this distribution, any distribution, is locally finite sum of distributions of this form, of functionals of this form. No, the order n can change, but in any finite interval it is bounded. So this is the general form of the functional over the space D. And what I'm going to do now, I'm going to explain that such functionals are in fact can be realized as non-standard and even infinitely smooth non-standard functions. So these singular objects are in fact just have much much simpler form if you go to non-standard setup. So so consider the following operation, modification. So this is the following thing. We have a function phi of x. It is a function with compact support, infinitely many times differentiable. Phi of x equal 0 for module x more than 1. Okay, phi of x more or equal than 0, and integral minus 1 to 1 phi of f dx equals 1. Something like this. This is the graph of this function. And now we consider if you take a function, say g of x, g of x can be arbitrary function. Let's say also L1. Yes. Then we can consider the following operation: g delta of x equals integral phi of x minus y divided by delta g of y dy. And here we have divided by delta. So what is this? Here is this function g, and we do the following. What is the function phi of x minus y divided by delta? So here we have the point x, and this is the axis y. Yeah? And now we take this function. This is phi of x minus y divided by delta times 1 over delta. So we shrink it in compress it in horizontal direction. We stretch in vertical direction, and so integral of this function with small support but very high, this integral is just 1. So this area is 1. So this is sort of averaging of this function g over small interval, now with this smooth weight. Yeah. So and we perform this operation for all x, and as a result we have some smoother function, yes, which is called g delta. Yeah. And now I wanted to let us see how it acts on the derivatives of the function. So d dx g delta of x. Let us do it. It is d dx of 1 over delta integral phi of x minus y divided by delta g of y dy. And let me introduce new variables, say z equals x minus y, y equals x minus z. So this is d dx 1 over delta integral phi of z divided by delta g of x minus z d z dy is minus dz, so it is times minus 1. So we have to differentiate this integral with respect to x equals minus 1 over delta. So d dx goes here. Integral phi of z divided by delta g prime of x minus z dz. So this modification goes to derivative. And now let us return to y variable. Z equals x minus y, so it is minus 1 over delta integral phi of x minus y divided by delta g prime x minus z equals y dz equals minus dy times minus dy. No, we have one minus here and other minus here. Let me erase it. And what is this? Equals g prime delta. Yes? So d dx g delta, g delta prime equals g prime delta. Yes? So derivative is here transferred to the function g. And similarly, we have g delta dm dxm g delta of x equals dm g dxm delta of x. So we modify derivative to of g to have modification of a modified function. So the operation modification with constant g, the width of modification, and derivative of any order are commuting. Okay, and now other thing which I would like to note that the g delta, if you look at the function g delta of x equals 1 delta integral phi of x minus y delta g of y dy, if you differentiate it with respect to x, dx, just a minute. Yes, let us look from other part. G delta of x equal, the only term which contains x is here, equals 1 over delta. We have to differentiate this. Any differentiation will bring one more delta. 1 over delta square integral phi prime of x minus y divided by delta, yeah? G of y dy. Phi was a smooth function with compact support, yeah? So its derivative is also smooth with compact support. So if g is in L1, for example, then this integral makes sense. So, and the result will be also, bounded integrable function. Yeah, and dm dxm g delta of x equals 1 over delta m plus 1 integral m derivative of x minus y divided by delta gy dy. So this means that this integral also is well defined. So this means that after such modification, the function becomes infinitely many times differentiable. Yeah. Okay, and now let me apply this operation, this modification in the following setup. So our functional has the following form. Phi is busy, so I like psi. So psi in Fc equals integral f of x and now let me write f c delta yes, exactly this. So now I use this modification to psi. Now, psi is already smooth, so why not? Equals integral f of x delta f derivative of c delta x dx. Now we know that m derivative of c delta is the result equals integral f of x so we write it is the psi m derivative of psi which is modified, yeah, which is integral f of x. What is m derivative? Times 1 over delta integral phi of x minus y divided by delta dy. It is phi m. Yes? No. Times psi m of y dy. And after all, dx. Let me write here. No, fx is an integrable function, so we can use Fubini theorem and write it in the following way. it is double integral, let me write, fx times 1 delta phi of x minus y delta psi m of y dy dx. And now we first integrate by x equals integral f of x times 1 delta phi of x minus y divided by delta dx. Integral another cm of y dy. Yeah? Just change the order of integration. And what is here? Here it is modification of f, function f, but I do it as a result will be f delta of y, because here integration over x and y remains here with free end, times c m of y dy. Yes. So if you here modify psi, then the result is the same as we modify this function f capital. Yeah. And now I, on one hand, on the other hand, if I consider the sequence of function psi delta, psi is function in C infinity, yes? Then C delta goes to psi when delta goes to 0 in C infinity. I mean, it converges together with derivatives of all orders. Yeah. So this function phi delta go to psi, and this means that in particular, derivative of order m goes to 0. Yeah? F psi delta goes to f psi as delta goes to 0. Okay. And now consider the family of functions, of functionals. F delta psi equals integral f delta of x psi m of x dx. Again, this family of functions. This is a family of continuous functionals on the space Cn. Yeah? F delta family of continuous functionals in the space Cn. Yeah? Continuous and uniformly continuous and so on. F delta goes strongly to F as delta goes to 0. So, goes strongly means that for any psi, we have the limit f delta psi goes to f psi. Maybe not uniformly, but it goes strongly. Strongly is this. F delta strongly goes to f. And now let us let us go to the non-standard extensions of this. Extension. Non-standard extension, we consider this family of functional f delta psi equals, but let me integrate it by parts because it is possible. F delta is infinitely many times different integral f delta m of x c x dx. Let's consider this. And in the equals, no, okay, in star u, in the non-standard universe, it has the following form: star f delta psi, or star psi, it is also star, equals minus 1 to the power m star integral star f delta m of x star psi of x dx. Yeah. So here star f, it is the functional non-standard functional. Yes. So it is the map of it is a linear functional. So star f delta, it is a functional from star c m to star r. Yeah. So everything become non-standard. Yeah. And delta star R plus. So it is non-standard positive number. It can be really positive, this means more than some standard number, or it can be infinitesimally small. It's all okay. And now here is the same, all clear. So star integral. So what is integral? Integral is functional, which takes a function and maps it into numbers. Yeah. So it is also some map. Yeah. So star integral, it is counter agent of this map in non-standard universe. So we have the following fact already, that f delta psi goes to f psi as delta goes to 0. Yeah. So if you take the non-standard extension, what happens if some function goes to 0 when argument, in this case delta, goes to 0? No, this function is the difference between this and this. Yes, this means that if the function goes to 0, then it is infinitesimally small when this argument is positive but infinitesimally small. This is what we have already established. So hence f delta psi is equivalent to f psi as delta is equivalent to infinitesimally small. Yeah? And in this case, we can do the following. Take delta, which infinitesimally small. Then we can write, then standard part of f delta psi is exactly usual standard value of this function. Yeah. Or okay. But this f delta psi has this form. Yes, or this form if we are in the non-standard world, and so we can write f psi equals standard part of the following thing: minus 1 to the power m integral f delta m of x psi x dx. If delta is infinitesimally small. So we have this formula. No, we can even move this minus 1 to the power m here. And we can not write it every time. It is a standard part of integral g delta to the nth derivative of x psi x dx. Simply so. Now g is also some integrable function, integrable in the non-standard sense. Yes, we take its modification, yes, and take the nth derivative. Finally, we write
is it G? The last one, last line.
excuse me?
Is it G?
It is G. I'm sorry. G.
How do you define this one?
Excuse me?
How do you define G?
Simply G is f or minus f depending on parity of n. Yes? So, what I wanted to say, that this formula gives us integral representation of any distribution. So, in fact, any distribution has this form with the appropriate function g. Yes? We can write g delta m equals say h. Yes? And so what can you say about this? G is just integrable function, but g delta is infinitely many times differentiable. Yes? If delta is infinitesimal, this does not change anything. It remains a function, an internal function, which is infinitely many times differentiable. So what does it mean? This means that we can differentiate this function h. Yeah, how to differentiate? We take h of x plus dx minus g of h of f divided by dx and take the limit. What is the limit? Limit is defined in usual epsilon delta terms. Yes? For any epsilon, which epsilon? Epsilon is non-standard. Yes, so both epsilon and delta can be infinitesimal. And then this differentiability holds because of transfer. Yeah? So this means that every distribution is in fact infinitely many times differentiable internal function. Yes, is defined by such an object. Now, for example, consider, I'm sorry, let me write, delta function. Just usual delta function on the line. How can you reproduce this function in our new terms? We did it last time. It can be done the following way. Consider the function h of x equals 1 over square root 2 pi square root of n e minus n x So this is just constant, which for any n makes the integral of this function equal to 1. Yeah? And hn of x. N is parameter. And now let us take n is infinite. N infinite number. Yeah? Then for any n we have the following integral hn x psi of x dx. So what is this? If psi of x is continuous function, then we can see that this function it has a sharp bump, yes, and then decreases fast when you go, yeah, and so this goes to just psi of 0 when n goes to infinity. Yeah. So we have this is our function psi. This is this bump function. Yeah. So the main contribution to the integral is from this short interval, which its length is about 1 over square root of n. Yeah. And when n goes to infinity, it shrinks to 0. Yes, and the result will be this limit. Yeah. Now, if you take n already infinite, yes, then this means that this integral will be infinitesimally close to psi of 0. Yeah. So we can write psi of 0 equals standard part of this integral hn of x psi of x dx when n is infinite. Yeah. So this way we recover the simplest and the most known distribution. How can you recover the distribution delta prime? Delta prime. In the standard theory of distributions, we write delta prime of x psi of x equals minus delta x psi prime of x equals minus psi prime of 0. Yes? So this is the value of this function. But we can write the following other formula. Psi prime of 0 equals minus I would say, right, psi prime of x, delta prime, psi of x equals standard part of integral h m prime of x psi of f dx. Yeah? So we can differentiate this function No, because it is the same, equals standard part of minus integral h n of x psi prime of x dx. Yes? And about this we know that it is minus psi prime of 0. But no, I don't say is it advantage or it is disadvantage or is it just feature that in this representation we can act straightforward. If we want to differentiate a distribution, you just differentiate this function. Because this function h prime, hn prime, is well defined in the non-standard setup. So we have it. We have many more strange functions than these. For example, what is the function square root of data x? Square root of data of x. Such functions can be met in works on nonlinear differential equations. Yes, and they, in the standard theory, they have no sense. Either it is 0 or has no sense. Yeah? And here you say simply, right, we have this function hn of x, h of x, or hn of x. You write I n of x equals square root of hn of x. So you can take these functions, yeah, and have at least an internal function which is represent this strange object. What it is depends. In fact, it is defined as asymptotic of such functions hn for finite n when n grows. We have this asymptotic, but in fact it is important that it can be continue to non-standard n, to infinite n's. In fact, very soon, on March 22, I'm going to talk in the Department Pizza seminar, and there I will tell about some exotic examples of this sort, which have interesting physical meaning, so you are welcome. Okay, and further. Okay, let me continue other topic. So it is one thing. Other thing which I wanted to tell today is the following. It is Peano theorem in the ordinary differential equations. So what is Peano theorem? Consider the differential equation dy dx equals f of xy, where xy points in some domain G. We have a initial condition y of x0 equals y0. So x0, y0 in G, and f is a continuous function in G. So this is just canonical initial value problem. And Peano theorem there exists some positive t and a function and a solution of so it is 1, it is still the problem to define x minus x0 less or equal than t. So it is a local existence theorem. So what can be said about this? Usually in the existence theorem, existence, uniqueness and so on, we impose more conditions on the function f. Yes, it should satisfy, for example, Lipschitz condition with respect to y, if you remember OD equals. Yeah. If this function f is merely continuous, then solution must not be unique. Yeah. No, let me give you example, which I think you know. Dy dx equals to square root of y, for example. Y of 0 equals 0. So we have one solution, y1 of x is 0, yes? y2 of x is x squared, because derivative of x squared is 2x, 2 square root of y. Now, we can also have solutions such that up to some point it is model y. It is 0, and from this point, x1, starting from x1, it is x minus x1 squared. We can also have this. So we have infinitely many solutions of this equation. However, the theorem says that solution exists. It doesn't say that it is unique. Yeah? How many solutions it can? Here we see some simple mechanism of generating of this non-uniqueness. There exists continuous right-hand side f x y such that solution is non-unique at every point of our domain. No, domain is, say, the whole plane. Yeah. So solution can be extremely non-unique. It can be non-unique at every point. So at every point it can decide go up or down. Yeah, but there should be something profound in the fact that in spite of this non-uniqueness, solution does exist. Yeah. No, okay. Let me start. Maybe I will finish in the last minutes, 15 minutes, maybe not. So we start from construction approximate solution. First of all, we define this T. We have this domain G, and we have this point at 0, y 0. So it is an internal point, so we can inscribe a rectangle in this domain with the center at this point x0, y0, where the function is continuous. If it is continuous in this domain, it is bounded. So it is, say, P0, model f of xy less than m in P0. So, and then we truncate a little bit this P0, let me put it in the center, truncate by two vertical lines, so that if you build here two lines with the slope m and minus m, then you have this domain, triangular domain, two triangles, which is completely inside this smaller rectangle. So this smaller rectangle is, say, just pi. So what is the significance of this domain? So if you have any possible solution of our equation, dy dx is f of xy, then its slope is between minus m and m. Yeah? So it cannot go out of this triangle of right or left triangle, depending on where you solve. Yeah? So here it is x0, y0. So it is x0 minus a, x0 plus a. It is y0 minus b, y0 plus b. Yeah. So the t equals a. So we guarantee that there exist solutions whose graph is in this and in this triangle and goes from the center to the right bound. So it is not somewhere exists solution, but we can guarantee that solution exists in this domain. It is one thing. Now we start with construction of approximate solution. So we have this segment x0 plus a, and let us divide it into n equal parts. by the point, say, x1, x2, and so on, it is xn. And let us construct an approximate solution which has the form of Euler broken line. So it is y0, so it looks like this. Something like this. This means that xk equals x0 plus k. Let me write h equals a divided by n, kh, and y, and we write yk plus 1 equals yk plus h times f of xk yk. Yeah. So the function is given everywhere f, but we take the value of the function at the left end of each segment. Yeah? And for intermediate values of x, we write if x is more or less equal xk and less or equal xk plus 1, we write yn of x equals 1 over h x minus xk yk plus 1 yk plus x one moment, it is linear interpolation equals yk plus x minus xk divided by h yk plus 1 minus yk. Yeah, so this is a linear function which takes the values yk and yk plus 1 at the point xk and xk plus 1. K equals 0, n minus 1. Yeah, so we have this function. And this function is defined yn of x. It depends on this number of the segments of partition. No, this is a very rough approximation of solution of equation. It is good sometimes, but usually is replaced, but practically it is replaced by more accurate approximate methods, but for our purposes it is enough. And now let us take n is infinite. Yeah? So we have a family of function yn of x. Yeah? So we have a family of function, and it is pretty possible to form an internal function yn of x such that n is non-standard, x x0 plus a, and yn of x in start R. So what can be said about this? So we have this butterfly figure, and if you consider the graph of yn of x, this slope of this all these linear functions is also between -m and n. This means that the solution yn, approximate solution, is also within this triangle. And then it means that this function yn of x already in its non-standard extension also satisfies this. So yn of x minus y0 less or equal than m x minus x0. First of all. Second, it is an internal function, and so we can take its standard part. Standard part yn of x. We have one. So what is this? We have to take all x in our domain. It is domain is star x0, so all non-standard number between x0 and x0 plus a. Yes. We have to, for each of these numbers, find the value of this function, and then take standard part of this and this. Yeah. Because the slope of all this function yn of x is less than m, this means that the result will be single-valued function. Yeah. Yn of x minus yn of x prime less than m mod x minus x prime. So for any m, so this means that it excludes this multivaluedness of the function. Because in our examples in the last time, we had a family of functions which the slope is not bounded, and therefore we had multivalued function as a standard part. So consider the function, say y capital is the standard part yn of x. And my claim is that this is solution. Y of x is a solution. Yeah. So how to prove that this is solution? is so the problem dy dx equals f of xy, y of f0 equals yz. We have this initial value problem, and this initial value problem is equivalent to the following integral relation or integral equation. Yx equals y0 plus integral from x0 to x f of t y of t dt. Now, so if a function satisfies this relation, then it satisfies this equation. Because, no, first of all, when x equals x0, this integral is 0, integral from x0 to x0, remains y0. And then if you differentiate this integral with respect to upper limit, we have exactly the value of this integrand at this upper limit. Yeah? So all well known. Now let me substitute here, instead of the function y of x, our function yn of x. No, first of all, it is late for you.
Oh.
Could you give me 10 minutes? Okay. So we write yx minus y0 minus integral from x0 to x f of t y of t dt yn. So let us put here this yn. Now let us do the following trick. I want to get some estimate for this. If n is infinite, it should be infinitesimally small. So now how to give the estimate? It is yn of x minus y0 minus integral from x0 to x. One moment. Let me see how I did it. Let us introduce it is xk plus 1. It is x. So let me write tau of x equals xk. If x in xk plus 1. Yeah? So tau of x is the left end of this. And then I write the following. Minus integral f tau of t y n of tau of t dt. So I replaced it with this. Plus, now I have to add integral from x0 to x f. Sorry. F and t yn of tau t minus f t yn t dt. Yeah. So what I did here, this is a piecewise constant right-hand side because tau of t is constant. Yes. Yes. Yeah. So when t between xk and xk plus 1, then this is constant. Yes, this is constant. This is yes. So if you look closely, then you see then this is all this is 0. Yes, because yn is a linear function. Yes, and this is integral of some constant. Yes, with variable right upper limit. So it is linear function, the same linear function. Yes, so I subtract this from this, and I have 0, and remains this. And now, what can I say? For n infinitely large, we have the following thing. That this point, tau of t, yn of tau of t, and t, yn of t are infinitesimally close. Yes? So f of tau of t, yn of tau of t, minus f of t, yn of t is infinitesimal. Yes? No, if it is infinitesimal, we have this integral. No, infinitesimal, it is not internal term. So it is hence it is less than epsilon. Infinitesimal is too strong. Let us say that it is epsilon. Yes, for given epsilon, for any given fixed R plus. Yeah, and if so, we have equals, say, in less model in less than integral x0 to x epsilon dt. Yes, because this difference is less than epsilon. it is less than epsilon A. Epsilon A, yes, epsilon A. No, it is equal. Yeah. So we have yn x minus y0 minus integral from x0 to x f of t yn of t dt less than epsilon a for any epsilon is r plus. And this means that hence standard part of this of in equals 0. Standard part equals 0. No, and this means standard of yn of x is a solution. So we found a solution. So the question here, if you recall the standard proof of Peano theorem, who remembers this proof? Okay, the standard proof goes as follows. We construct a sequence of this approximate solution of Euler lines, Euler functions, yes, and then we use their pre-compactness in the space of continuous functions because they are uniformly bounded and equicontinuous. So we can extract a convergent subsequence. So the proof is not much longer than what we did here, but it's interesting where did this compactness and so on go. No, it is somehow distributed among the structures which we used, among the notions of internal objects and so on. So here we have no, in fact I cannot really tell you now what is the real counterpart of compactness here. Yes, somehow it should be equivalent proof, but it is not visible instantly. So if, say, we had these tools of non-standard analysis before this theorem was proved, maybe we would have different proof and the compactness considerations would not be used here, at least in the direct fashion. No, okay, so let me finish today and continue different examples of non-standard reasonings next time. And I ask you to decide which Friday is good for makeup. Okay?